Welcome, everyone, to this week's Zoom for Thought, where we will have Tom Grubb tell us about some, not all, of the differences between the letters D and O. Take it away, Tom.
Okay, hello. Thank you, Vaki and Sam, for organizing. To the people watching on YouTube, thank you to our sponsor, NordVPN. So today I'm going to be talking about some topological data analysis. If you've never heard of it before, that's perfectly fine. I plan on introducing it at least at an intuitive level and kind of starting from nothing. So the standard kind of usual caveats apply. I'm not a topological data analyst. I don't really know much about it. I just kind of read some of the papers. And also I just like complaining about stuff at this point. So take everything that I say with a grain of salt. Okay, so some motivation, obviously data analysis and machine learning are like the bee's knees over the last 10 years or so. And we've gotten a lot of good things out of it. So if you've ever had your credit card, fraud detection alerted and save you money and time and a headache, computer vision has been very useful for things like medical imaging lately and diagnostics. There are even some quality of life things like chatbots that are helping, for instance, elderly people order groceries kind of automatically. A lot of applications of machine learning, and a lot of them are pretty good. But one of the big problems with machine learning nowadays is that all of the techniques are incredibly black box, in the sense that if you try and explain to someone the results of your model, it's nearly impossible. So modern ML techniques are very good at making predictions, but they're very bad at explaining why they are making that prediction. So if you've never seen what like a neural net looks like, this is a very basic example. The idea here is that you would have kind of 3 input parameters on the left-hand side, and you want to make some sort of binary yes/no classification based on that input. So maybe it's like someone's age, their race, and their income level. And the yes/no input is, did they vote for Biden in the last election, or something like this. And nowadays, kind of the standard technique is just to throw a neural net at it, which is just a technique of function approximation. So you just have this setup where you transform your input parameters through a series of linear maps and what are called activation functions. And that turns your 3 inputs into some combination of those 3 inputs, and that puts it into a new layer, a hidden layer of data. And then again, it stacks on top of that another layer of linear transformations and what are called activation functions to create another kind of hidden layer of data. In general, dozens of these are stacked on top of one another. And at the very end, you have some way of deciding yes or no based on that last hidden layer. The point being, tracing through from left to right is nearly impossible. So if I started over here with your income level, well, that's being taken into account into several linear maps, being passed through several nonlinear activation functions, and then finally being used to make a prediction. So this is not like something like linear regression, if you've seen that, where it's just very easy to read off the coefficients. And I emphasize that this is a basic example. So here is an example of a layered machine learning kind of infrastructure, where each one of these little boxes is like a much more complicated version of the picture I just showed. So this is from some computer vision. So you should think that you're inputting a series of pixels and you're following this flow chart and then getting an answer out at the end. So this is from a state-of-the-art handwriting digit recognition, so numbers 0 through 9. So this is currently the state-of-the-art architecture for recognizing digits. And it's just impossible to parse. So again, another example, this is what these things kind of look like under the hood. And if we zoom in, it's a little hard to see, but like you can see the number of parameters that you're learning is on the order of millions. So 5.3 million kind of hidden parameters that are in your model. And there's just no hope, right? Our input was 28 by 28, so under 1,000 features, and we're upscaling to 5 million features. There's no hope of explaining that. And believe it or not, this leads to a lot of problems. So not just like the kind of doomsday problems that you might think. So for example, this is a funny image that actually Patrick shared with me last year. So this is an example of a deep image classifier. So deep in the sense of like neural networks. What it does is it takes in an image. So this is like an apple, and it outputs what it thinks it is. So here it correctly is identifying that this is a Granny Smith apple with like 85% confidence. And here is that same Granny Smith apple, but with the word iPod written on it. And now it is over 99% confident that this is the physical like Apple iPod. These kind of attacks, they're kind of funny to look and laugh at, but if you think about things like Tesla's automated driving systems, right? And you think about what would happen if someone, right, sprayed graffiti on a stop sign, and instead of stop, they said go. You can see why you really need to understand a little bit what's going on under the hood, and you need to prevent these kind of attacks. There are also a lot of serious problems that aren't really that funny to look at. So for example, again, going back to computer vision, facial recognition historically is trained on largely white individuals. And so it's better at recognizing white individuals. And so drastically higher error rates for facial recognition for Black and Asian individuals. If you look at things like large language models, if you're interested in natural language processing, these have again and again displayed biases based on religions, based on genders. Again, the idea here is that these language models, they're learning human interactions, human texts, and there's a lot of biases in human texts. And if you don't have ways of preventing that from kind of going into your machine learning model, it's just going to learn those and convert them into predictions. And then finally, another example with respect to using machine learning to determine credit limits. This was an example of a husband and wife who both applied for the credit card where this machine learning was being used, and the wife was deemed significantly less creditworthy, again, with no explainable reason why. Okay, so all of these things are things that I hope we would all want to avoid. You know, at least we can say that these mistakes are just from small startups who probably don't know about the technology and probably not impacting anyone, right? We might hope that was true, except this bottom example came from Apple's Apple Pay credit card. This middle example is coming from Google's like BERT language model. And this example at the top is being used by, for instance, US Customs and Border Patrol. So these are not small startups making these mistakes. These are right, leading the industry tech companies who aren't getting this right. So as you might imagine, this has led to a lot of interest in what is known as explainable ML. People call it explainable AI, artificial intelligence, but I have a problem with that, and I'll maybe talk about it at the end. But the point is that you're just trying to explain what's happening with your data analysis. And that is generally the starting point for today's talk. So what we want to do today is a little bit of an exercise in computer vision. The idea is that we want to develop a white box or explainable classification algorithm, which uses explicit techniques to classify an image as one of the English letters. So what we might have is, as input, we would have this image on the left-hand side. We would feed this into some automated algorithm that hopefully we can explain. And then the output of that algorithm is, classification into one of the English letters. So here we're taking like a physical drawing, right? To humans, this looks kind of stupid, but again, the emphasis is that this is for a computer to take an image into a piece of text, and so it's not exactly trivial. Are there any questions at this point about the setup or what we're trying to do? I'm not reading the chat, so just yeah. Okay, so just as a reminder, so there's 26 letters in the English alphabet. For simplicity, I'm going to assume they're all capitalized, and this is kind of the pictures that we're trying to recognize. So I've just listed them all here, and kind of the initial observation. Oh, whoops, sorry, I forgot the order of my slides. And we're going to take an image, which is kind of supposed to be one of those 26 letters. And before we get into analyzing the image, we have to talk about what an image is in the first place. So an image is a collection of pixels arranged in a grid. So you can think of kind of like a chessboard, if you will. And within a pixel, the color is constant. So those pixels are lined up together, and it's like a fill in the dots of colors. The pixels are so small that you don't really see that they're constant rectangles, but that's all it is. And there's various ways of representing the coloration within a pixel. So there's RGB, red, green, or red, blue, green, red, green, blue, whatever. Each pixel has 3 intensities associated to it. So you can think of this as like a 3-dimensional kind of matrix, just representing the intensity of red, blue, and green. A simpler version is just grayscale, where you have one number associated to a pixel, which interpolates from, 0 would be white, 1 would be black, and a half would be like a light gray color or something. We're going to be making the simplifying assumption that the pixel is actually just black or white. So this is like a binary representation. It's either entirely on or entirely off. We don't lose a lot of generality, because if you think of like handwriting, this is mainly the situation you'd be in the first place, and you can easily kind of convert downwards. So you can go from RGB to grayscale, and then you can go from grayscale to black and white fairly easily. So of course we're losing some generality here, but not in a serious way. So with this, we can represent our image in one of 2 ways. So either a binary matrix, 1 or 0, whether the pixel is on or off, or you can give kind of a sparse representation where we think most of the picture is white. And so because of that, we only remember the pairs that are not white, or the pairs that are black. So what this might look like is, here would be an image which is 3 by 3, right? 3 pixels. There are 3 pixels by 3 pixels, so 9 total pixels. 3 of those pixels are turned on, right? This would be the binary matrix. And this would be considering it as like the XY plane, and as a scatter plot, kind of where are the locations of the on pixels. So I'm not, right, this is not the matrix index representation. This is me thinking of this as as R2 and looking for the center of these pixels. Okay, so with that in mind, we can move to the motivating observation. So the motivating observation for this algorithm is that if you can detect holes in a letter, then you can already do some classification. So there's one capital letter that has 2 holes in it. That's the B. There's 6 letters that have 1 hole in them. And then there's 19 letters that are effectively combinations of line segments with no holes. And to be precise, what I'm saying is that if you have some letter, it's very weird to think of a variable for a letter, because variables are all letters. I really wanted to say like if 3 denotes an arbitrary letter and flip that on its head, but it didn't. So if chi denotes an arbitrary letter, then if you can measure like the rank of the first homology of chi, you already have kind of a weak classification into one of 3 boxes. Now, of course, what you're saying is this is not going to work. there's a lot of letters, and one of those boxes had 19 letters, so it'd be a very stupid kind of handwriting classification system. And I would agree with you, but if you think a little bit longer, you can move to kind of a second actual motivating observation, and that is you don't just have to work with the original image itself. So if you imagine those images kind of sitting on the x-axis and you reflect across the x-axis, you can see kind of my original observation and motivation for this, and that is when you reflect across the horizontal line, we've split up the one-hold letters into, for instance, this A, which reflects into something with 3 holes in it, and for instance, the D, O, and P, which reflects into something with only 2 holes in it. So what you're seeing is we're kind of utilizing the geometry of the letter on the screen in front of you. We're not just topologically thinking of all of these as circles, right? We're not doing any kind of homotopies where we'd collapse the segments in. We're actually keeping those there and taking advantage of them. And this actually lets us get some mileage into an actual good classifier. So at a high level, what does the classifier do? So it takes a series of pixels, right? Initially, it's just going to take an image of a letter. It's going to view it as a scatter plot in R2, and it's going to measure the rank of first homology. Again, if you don't know homology, it's just going to count the number of holes. It's going to do some sort of geometric transformation, not in any mathematically precise definition of geometric, just like, you know, use your imagination. And it's just going to repeat this process until you've uniquely separated the letter. So the only thing we're doing is measuring holes and then doing things that look like maybe reflections and some additional operations. In other words, if you are familiar with machine learning a little bit, I'm basically just describing a decision tree, but the branching rules are very explicit. So what you can imagine is you have some letter and you feed it into kind of the top node of this tree, and you're gonna do some test to the image on that node. So for instance, the first test is simply going to be to measure the first homology group. If it's ranked 0, you go down and to the left. If it's ranked 1, you go down. If it's ranked 2, you go down and to the right. Right? The green nodes are supposed to be the leaves, the terminal nodes. That's where you've actually made a classification. Right? If I measure first rank homology and I get 2, then the only letter that could be is a B. And so I'm done. But if it's rank 1, then I need to do some more operations, continue to measure some more homology, and work my way down until I've entirely separated the letters. So these decision trees, they're common techniques in machine learning, but usually the decision trees are kind of generated automatically using some sort of descent techniques to kind of maximize or minimize whatever, it depends on your viewpoint. But usually these branching rules are kind of generated for you. And what I'm saying is I like the idea of a decision tree, but again, I want this to be explainable. So I'm just going to tell you exactly what happens at every one of the nodes. Okay, so this is the high level of what we're going to try and implement. But the big thing now is how do you get a computer to measure homology? So yeah, that doesn't sound very easy, especially if you kind of know what homology is. How can you actually compute that automatically? It's not so simple, but it turns out it kind of is fairly simple. So this is a subset of what we would call topological data analysis, or TDA. The context of topological data analysis is to try and recreate the shape of a source of data given a discrete sampling of that data. This doesn't really make sense in words, so I have a very beautiful picture. Right, as an image or as something on a piece of paper, the letter A is like a continuum of ink, right? It's an actual shape on the plane, you can imagine. So it makes perfect sense as a topological space. But if you take a picture of that, computers can only handle, right, finitely many bits of information. They can only handle finitely many pixels. So in principle, when you take a picture of something, you've discretely sampled from an underlying geometric shape. So, right, you should think of this A as a, like, imagine it wasn't drawn by a 2-year-old and it was actually like an A in front of you. And then I've just kind of uniformly sampled along this A a bunch of points. And like this middle image is actually what's on your computer when you have an image of an A. Even though it doesn't look like this, that's physically what's happening, is you just have these point particles. And we want to try and somehow now go back to the actual underlying A itself instead of our sampling of the A. So this kind of question mark is in some sense topological data analysis. This is way too much to ask for in general. So instead of asking for, can we recreate the entire shape itself, usually what we do is we try and approximate the shape. So for example, in the setting above, where we have kind of a sampling of points chosen from some space X, can we approximate any of the homology groups of X just given this sampling of points? Or even more basic, can we approximate the rank of the homology group? You can imagine things like torsion would be very hard to find, but can we get the rank of these homology groups? Again, if you don't know what HI is, I'm not going to explain it, but the thing to keep in mind is that we're only going to apply this to a shape in the plane, in which case I only care about I = 1, in which case you're literally just counting kind of gaps in the picture in the intuitive sense. Okay, so the main technique of doing this, it came out 10 or so years ago. It's very new. And it goes by the name of persistent homology. And the problem is that you can't just compute homology of a set of points. Well, I mean, you can compute the homology of a discrete set of points, but it's just uninteresting, right? You would get n copies of z in rank or in degree 0 and nothing in higher degree. Right? This is just a scatter plot, and that doesn't have homology. So instead, what we do is we have this idea of persistent homology, which in some sense is going to use those discrete set of points P1 through Pn as kind of a starting point for an approximation to this space. And then we're going to grow further and further approximations to the space over time. So the idea is we're starting with these kind of seed points P1 through Pn. And you should think of this number R as like a time parameter. For each time, we're going to associate a new space P sub R. I guess I should have used T, but whatever. And what you should imagine intuitively is that PR is obtained by thickening P by R, a radius of R. So precisely what I'm trying to get across is you're starting with P sub I, and you're replacing that with a ball of radius R around P sub I. So what does this look like? Well, you would have this discrete set of points on the far left at like time 0. And then you would thicken each one of these kind of point particles into a ball of radius 1. And you can see here, I've started to recreate the A shape fairly well. And you can see here that if I worked on this time = 1 shape, I actually would start getting some homology back. Then what happens? Well, you continue to grow your space, and these balls get thicker and thicker. And you can see here now that the single hole in the middle of the A, it's actually closing up. So we can still kind of measure some homology here, but it's not quite as apparent. And then finally, it's maybe some good intuition. What would happen if I let this go to infinity? Well, effectively, I would just get one huge black blob of ink, right? All of these balls would be way too large to understand the underlying geometry of your original A. So the idea is to kind of analyze the evolution of these spaces as time increases. You're going to start with something not very interesting. You're going to end with something not very interesting, but along the way, hopefully you actually, are able to get some information out. What this formalizes to is the concept of a persistence barcode. So the idea is for each base piece of R, we can compute homology of piece of R. Okay, and so that gives us kind of a function from time into, right, homology groups. These homology groups evolve over time, and it's really important to kind of internalize what this looks like. So let's do another picture. So again, we start on the left with just our point particles. And if we try to calculate first homology, there aren't any actual physical holes in the data because the points are too small. So we start with no first homology. And let's skip over to the very right. We also end with no first homology because we're ending with just a contractible blob, right? There's no holes in it. But in the middle, what we're going to see is that as we kind of balloon these points up bigger and bigger, we will start to pick up holes. Now, the problem is some of these holes are just going to be, due to noise effectively, right? So if you look at like the bottom left of this A here, you can see I have something that kind of looks like a circle, but it's not actually like a circle in the underlying space. It's just a circle in kind of generated by noise from the sampling of that space. So I'm going to get a few noisy holes, but I'm also going to get the honest hole in the middle of the A. The problem is, how do I separate kind of the noise from the honest holes? Well, that's where the name persistence comes in. The idea is that the actual physical holes in your geometric space should persist over time as these spaces evolve, whereas the noisy holes will very quickly be filled up by others, by space, by points. So the noisy holes, if you kind of track the birth and death of the homology classes that you get, the noisy holes will, be born at some time and will die very quickly after, whereas the honest hole will have its birth and then it will persist for some time and finally die out. So this is what they call a homology barcode. It is essentially for each homology class you pick up along this evolution, you track how long it survives. And then by analyzing this barcode, we have some idea as to the underlying homology of the space that we're trying to approximate. Okay, so let me take a quick break there again and just see if there are any questions about the idea of persistence homology or what we're trying to compute.
Is it easy for the computer to tell that C1 hole is actually C1 and maybe it's not, maybe it's C2, or lost track of which hole was which kind of thing? Or does it just matter, I guess, the number of holes at this point?
Yes, I will. Yes, for now, for intuition, just imagine yes. And then later, I'm going to quickly go into some of how this works, and it'll be easier to explain then.
Oh, cool. Thank you.
Okay, so hopefully these pictures are making sense. And this really is, like, if you just want the intuition on topological data analysis, this is all you need to understand. But if you actually want to implement it, then you need to know how to make this work in practice, right? So even with the intuition, we're still working with an infinite amount of data, right? We're working with like closed disks in space. Even though those disks were generated from a finite set of seed points, As soon as those disks have positive radius, I'm right back to an infinite amount of data. And you can't have a computer understand that. So the idea is that instead of working with an actual geometric space in the plane, what we're going to do is create an abstract simplicial complex with vertices given by our initial data points. If you don't know what abstract simplicial complexes are, I'm sorry. The idea is that the K face is included in the time t simplicial complex. Well, there's various ways of doing it, so I'll give you two. So the first way is called the Vietoris-Rips complex, and that is you're included in the complex if and only if all of your pairwise distances are less than t. Okay, and I'll draw a picture of what this means very quickly, but what you should imagine is that, for instance, if I have 2 points, then as soon as the time evolves past the distance between those 2 points, I'm going to draw an edge between those 2 points. And if I had 3 points, I would kind of initially be drawing pairwise edges between those 3 points. And then as soon as they're all close enough together, I'm going to draw the edges and also like the face in between the edges. There's also what's called the check complex, which is instead of looking at pairwise distances, you look at everything kind of all at once. So you take the ball of that radius and see if there's an intersection in that ball. Again, I think this is better just to draw a picture. So let's imagine we just had 4 points and we were building a simplicial complex on these 4 points. So the idea is we're gonna kind of fill up these points with air and turn them into balls and see when those balls start intersecting. So you can imagine that the first thing that are gonna intersect are the 2 bottom exterior points with the first kind of middle, or the only middle point. So, right, my simplicial complex is going to be 4 vertices for a while. And then as soon as the balls get a little bit big enough, I'm going to connect those 2 vertices and those 2 vertices. What that means is I'm going to start with this simplicial complex, which is just a bunch of 0 cells. And then I'm going to take that same complex and add these edges P24 and P34. I should have numbered these, but so P24 is one of these and P34 is one of these. Then what happens is, well, time's going to evolve again, and eventually like the exterior equilateral triangle are going to get close enough to one another. But you can imagine. Oh. Sorry, Siri's listening. Right, you can imagine as soon as this top point connects to this bottom left point, it's also going to be connecting to the middle point. So as soon as I pick up this exterior edge from top to bottom left, I'm also going to have to fill in the edge with a 2-dimensional face in the simplicial complex. So that's, you know, I kind of skipped over some of the intermediate steps, but this is the 3rd step I've drawn, where now I have all of the 1-dimensional edges in these places, and then a few 2-dimensional faces in orange. And then finally, what happens, you know, at infinity? Well, the balls are going to be so large that everything's going to intersect with everything. So I throw in all of the faces that I can possibly have on 4 vertices, and so I get a kind of solid tetrahedron. Now, again, I want to stress that the geometry is actually not anything you work with. You work with these abstract combinatorial simplicial complexes because this reduces things to a finite set of data that a computer can understand. But I think the picture hopefully kind of explains what's going on. One reason the geometric intuition is not so great is because right? So every abstract simplicial complex has an embedding into a Euclidean space, but the dimensions aren't necessarily going to be what you want them to be. So for example, if I started with 4 points in the plane, the maximal simplicial complex will be 3-dimensional. So I have to bump up a dimension to think of this geometrically, but that's fine. The key point is that if you think of things in terms of the abstract simplicial complexes, you actually have a discrete thing that you're working with. And then if you've taken 290 already, if you've taken topology, you know that from a simplicial complex, you can compute simplicial homology entirely algorithmically, at least like in principle. Right, the chain maps are just, they are what they are, and you just write them down. So it turns out that from this abstract simplicial complex, you can compute simplicial homology just by writing the definition of the chain maps down and doing some linear algebra. In principle, really, it's like linear algebra over Z. Again, that's just some technical details, but if you're interested in looking into this, right, the key technique is what's called Smith normal form. And so Sam, I guess to your question, because we start with a labeling of these vertices, and those vertices, the labels of the vertices are the same over time. That's kind of how we can keep track of the homology classes that we're picking up and killing off as time goes on, is that this gives us a way of keeping tabs on that.
I see, that makes a lot of sense. Yeah.
Is it, Tom, is it really better to work with Z coefficients? You just work with over a finite field or a Q or something?
Yeah, I think, I don't know. I think in practice that might depend on what you're doing. I think the way it's presented most of the time is with Z coefficients. But yeah, you're right that like in practice, when you get into these calculations, it probably would be better to do some sort of simplification like that. But I think that would be kind of context specific. Okay, so this gives us our desired association of, we started with our kind of seed set of points. We evolved them over time to get well, you can think of this as a topological space PT, but really we got an abstract simplicial complex. And then from that, we can compute simplicial homology. And so what we would do is we would kind of sample a set of time points from 0 to 1 billion or whatever, and from that compute barcodes. And a key point, again, just to bring everything back together, is that actually there's something called a nerve theorem, which says that in a sense that can be made precise, right? The abstract simplicial complexes that you get out of these processes, you can embed them into a Euclidean space. And in a suitable sense, those are actually homotopy equivalent to the intuitive way of thinking about it, where you just take a point and thicken it into a ball of radius r. So in particular, we're computing kind of the same homology that we were when we thought about things intuitively instead of precisely. Okay, so we can now go back to the future and apply TDA to our algorithm. So, right. Now we have a way of actually approximating kind of first homology of our images. I'm not going to go through the entire alphabet and tell you exactly how each letter gets kind of separated from one another, but I thought I would just choose some kind of illuminating examples and just draw them on the slides. So one example that I think is pretty interesting, right, is how you can separate between a D and an O. Right, so D and O are very similar to one another. The key difference is, right, the D has two kind of right angles on the left, whereas the O is curved all the way around. And so if you think about what this does, what we can do is I can reflect these letters kind of on over their leftmost point, if you will. And what we see is that roughly speaking, the D should be kind of lining up flush with one another, whereas these circles are just going to kind of meet at a point. And then we can reflect across the x-axis again. And again, because the D is kind of roughly flat out that axis, these should, in an ideal scenario, be kind of sitting flush against one another. Whereas the circles, right, you have this kind of piece that's missing that actually turns into a fifth homology class. Right, obviously the four homology classes are kind of similar between the D and the O, but in a suitable sense, the O is going to kind of miss out on a chunk when you do this rotation procedure. Now, obviously, as soon as you move into handwritten things, you have people with terrible handwriting, and right, this D is probably not going to actually look like that. So right, you have kind of backup techniques of also separating the D from the O using different sorts of reflections, but I think at least in this idealized scenario, this is a nice example showing how you can kind of separate the angles of the D versus the curve of the O. Another one that I think is kind of interesting is V and U. So V and U is very kind of similar to D and O. They're basically the same kind of stroke. So this one was kind of difficult to think about, but what I figured I could let myself do is utilize again the geometry of whether something is straight or curved. So what you can do is you can look at the V and you can look at the U, and you can kind of extract the top left in a way that can be made precise, the top left pixel of the image. And then again, in a way that can be made precise, you can kind of extract the bottom middle pixel of the image. So you know all of the pixels in blue. So from that, you can kind of get the center kind of horizontally where the center is, and then you just look towards the bottom. Anyways, you can focus on these 2 points. And then the idea is that a V is simply a straight line segment between those 2 points, whereas a U is a curved line segment between those 2 points. And moreover, once you have this image in your computer, you can also interpolate between 2 points. So we can add the red line segment, we can superimpose that on top of our image, and then again, continue to compute persistent homology. What we should see is, right, for the most part, the red and blue lines will overlap for the V. Maybe we'll pick up some noisy homology briefly, but again, in principle, nothing that would be as persistent as this homology class in the U. And then finally, another example, something like a T versus an I. So again, the idea here is we can look at kind of the extremities of the letters. So we can look at, for instance, the leftmost pixel. Again, we can superimpose some additional lines onto the image. And what we'll see again is that the I is going to have some amount of homology here, whereas the T won't. We could even repeat this to be doubly sure kind of on the rightmost pixel. And again, ideally, we would see a similar thing.
Does the algorithm have a method for deciding like when to use these extra more complicated tricks, or does it just sort of throw everything whenever it's confused?
Yeah, so this goes back to that kind of tree drawing I had near the start. So everything is kind of hard-coded into which test is applied when. So like if you passed test A and then you failed test B, we're going to run test D or something like this. In principle, you could, as you were saying, you could also just apply all of the tests to the letter, and that would give you like kind of a, well, it wouldn't be a binary vector, but it would look something like that. And then from that, you could also make a decision. And you would probably do better that way. You would get more information, but for simplicity, I just kind of hard coded the way down. Okay, so that's for the most part it. So some caveats, obviously, I mean, you've probably all realized this, but I'm too lazy to actually bother testing this on a lot of handwritten symbols. It does very well on standard computer fonts. It doesn't do well on something like Wingdings, but like Times New Roman, it's fine. And I have had like, you know, my family write a letter, and so far it actually does fairly well. But to be honest, like it probably won't come nearly close to the accuracy that you would get with an actual neural net. On top of that, it requires much more upfront effort to implement this, right? So nowadays, with like packages, you can just download things that let you train and run neural nets and classifiers super easily. This requires a lot more effort, and it's hard-coded effort. So you can classify letters with this, but it wouldn't help you classify numbers. So it's not very useful in that sense. And then finally, it's actually pretty slow in general. So there's lots of linear algebra that's going on with very large matrices. As soon as your image is like, you know, a lot of, or as soon as your image has too many pixels in it, the persistent homology calculations take a lot of time. So in practice, this algorithm probably wouldn't ever be used, but it has some positives. So at a granular level, I can tell you why it made a certain prediction, right? I did some sort of reflections and through some line segments, calculated homology. And additionally, kind of based on that, you can look at where it's getting things wrong, and you can just add additional tests to help fix common mistakes. So in that aspect, I kind of like it. And additionally, it requires no data to train. So, right, neural nets require thousands and thousands or hundreds of thousands of data points to be able to do things effectively. I started this with just my own knowledge of the English alphabet, right? So although it was more work implementing it, the data gathering was completely absent. Maybe in the last 3 minutes or so, I want to just give some closing remarks. So the point that I want to emphasize is that currently there's really a heavy over-reliance on just raw function approximation in ML papers and ML work. Right, what we have is just incredibly powerful GPUs and huge data sets.
There's a question in the chat.
Oh.
Let me, for the record, read the question in the chat. It is, which software packages would you recommend for computing consistent homology?
Yeah, there's an open source thing called Ripser, which works with Python, which is what I implemented this in, RIPSER. Right, so the idea is that you can train huge neural nets now and do very well at predicting things, but it's so far from anything that would actually be like artificial intelligence that it's really like kind of frustrating. So in fact, even artificial intelligence as a buzzword was just like invented in the 80s to help Stanford get funding for its AI lab. Like it doesn't really mean anything. And our current state of ML is not artificially intelligent. The idea is that current ML, all of the underlying knowledge is like implicit, right? So imagine you had a diner and you wanted an October specific menu, right? And so one person has a huge computer and they train it on millions and millions of data points, and they say you should sell apple cider and pumpkin pie. That's not artificial intelligence, right? Intelligence would be saying like apples and pumpkins are in season in October, and it's cold in October and people like being warm on cold days, so you should sell hot apple cider and pumpkin pie. Like that kind of logical reasoning would be intelligence, or at least in my opinion would be intelligence. And in some sense, this knowledge is encapsulated in the knowledge of person A, but not in any meaningful, useful sense. And so I'll just leave with this slide that I think it's important to move, we shouldn't throw the baby out of the bathwater and just forget about neural nets and these very powerful techniques. But I do think there's a lot of gaps in the techniques that are currently used. And I hope that's something that will be addressed soon. If you're interested in this kind of thing, one thing you might look into are knowledge graphs and the semantic web. So I think I'll end there. Thank you for coming and thank you for listening.
All right, let us thank the speaker. Are there any questions?
Yeah, so one obvious question is, why am I Marty McFly and Jason Doc Brown?
Well, I think you actually kind of look like Marty McFly. Don't you have a lot of orange vests?
That is the most plentiful color of vest that I own. Yes.
Yeah. So I think that explains it.
I think it's also, I work, I work more closely with Scott, so I'm more likely to say, great Scott.
Yeah, that too. We'll go with that.
Yeah, Sam doesn't drive too, so
All right, Greg's mic doesn't work, so I'll read his question. It seems to me that the persistent homology measures not just holes, but the size of the hole. I was going to ask this too. Can you comment? Does it have to be scaled somehow?
Yeah, that's a good point, right? It will definitely tell you about the size of the holes, and that's in part why like the noisy holes kind of go away so soon, is that they should be very skinny. And so yes, that actually is kind of in practice a problem, because to get measurable H1 classes, not only do you want a hole, but you want it to be like circular holes. So if your hole is like a very skinny rectangle, so if you like skewed your shape to be very tall and your hole was resultingly very tall and skinny, the skinniness of it will kind of not let that hole persist very well. So it has to be kind of big in every direction, otherwise it's going to get filled in. So yes, in principle, that would be something you have to keep in mind. But for the most part, I just kind of worked from the start with letters that are of the right size and shape and went from there. But yeah, if you were implementing this in practice, that's definitely something you would take into account.
Any other questions?
Yeah, on a similar note, is there any way to so when you're doing sort of standard machine learning, you end up with this sort of like prediction percentage that you can find some way to classify this is more likely to be an A than a B, where you can get some we're not sure. The decision tree in this seems to take that out of it too. Am I wrong on that?
No, you're correct. So this would tell you whatever its guess would be, it would one, make a guess, and two, it would be essentially 100% sure in that guess. This is largely because I was too lazy to do any better than that. But in principle, you could imagine taking into account the previous question, the size of different holes you get at different points in time, or at different steps in the transformations, and you could take those into account to be I'm very positive this is an A, or I'm only kind of positive this is an A. But this is more of a proof of concept than anything. So
Anyone else? JJ asks, is your code on the web?
Yes, but you shouldn't look at it. Yeah, it's on GitHub. You can look at it if you know what my GitHub account is, but it's incredibly messy. Yeah.
Mysterious. All right, anyone else? Okay, I actually have several questions. I think I can collapse them into two. The first one is, do you know if there are any like quantitative statements or versions of the nerve lemma that maybe take into account if you have an underlying geometry as you do in this situation?
Probably. I don't know. It's been a while since I looked into. I feel weird.
This is hilarious.
I don't know. I never bothered looking too closely into that.
Sweet. I bet, because I could either bet it's extremely hard to prove things like that or surprisingly easy. So
Yeah.
interesting. Okay, my second question is, give us your rant about the term explainable. I don't think that ever came out. It came out implicitly, maybe.
Oh, the rant was on the term AI, artificial intelligence.
Gotcha.
Which kind of came out. Yeah, people just think very good predictors are intelligence, but that's not really.
Yeah. Actually, very related to this. I would think the goal with getting something explainable, or like the reason we want something explainable, is essentially that we sort of don't know the answer at the end, and we want some way to for the AI or the ML to tell us how we should have arrived at the answer that it arrived at. But it seems like in this example, we knew what the answer had to be, and we had to kind of give it a little bit of structure for how it did its training. So that also kind of strikes me as an extremely difficult problem to solve, of like, you really don't know anything about the answer at the end.
Yeah, I think a good example of this is if you look at like Deep Blue or any of these AlphaGo, like the things that have effectively crushed humans at chess or any kind of strategy game. So humans actually have gotten a little better at chess by studying how computers play chess, but not a lot better. And it's almost exactly for that reason, because if you try and analyze the moves that a computer is making in chess, it's thinking like of 8 million different possibilities 10 moves away, and it's just maximizing over all of those possibilities. Whereas like all of the human opening theory in chess is like, well, you have a fianchetto bishop that's going to be pointing at your king. So yeah, like I think that's a very prime example of where something like explainable machine learning would be like cool to see how a computer would kind of justify the moves it's making or something like that, but we're just not at that stage.
Yeah, that sounds like a really good test round. All right. Thanks a lot. Anyone else have any questions?
Yeah, I have one other question. Have you thought about using this to digitize books, like printed books?
Now he has.
Oh, you didn't hear the question.
Oh, no.
He asked, have you thought of using this to digitize books?
Oh, no.
All right, earth-shattering one there. Any other questions? That would be kind of fun though, to digitize a book. Would it take like years? All right. And, oh, go ahead, Sam.
Yeah, as long as it's a short book, you know, like Bob jumps over the cat or whatever those.
True.
Yeah, I could do that, I guess.
But yeah, I think we should thank Tom again for speaking.
Yes, indeed.